This is a step-by-step tutorial on how to integrate ordinary differential equations in Python. So we're going to start off with a simple example, and that's going to be just a first order linear system, and I have something like this: d tau times dy dt equals negative y plus k times u. Okay, so in this we have two parameters. That's called time constant. Okay, and then this will be our gain, and we just want to set up and solve this maybe for an input step change in u. So maybe u is our input, okay, is going to have a step input, and then we want to see what the response will be. So that might be y, for example. So let's just give our time constant a value of 5 and our gain a value of 2. And so what I'll do is let's just go ahead and start with the Jupyter. I'll do Jupyter Notebook. Okay, I'll just start up, and then it'll be able to edit in my web browser. If you want to use the Jupyter Notebook, you can also go to try.jupyter.org, and sometimes they're all full. So sometimes you need to go to and download it. Download Anaconda. Okay, so if you haven't done this already, just go and download Anaconda from Continuum.io, and you can get IPython. Okay, so what you'll do is once you have it downloaded and start Jupyter, just go ahead and do new and create a new notebook. And the first thing that we need to do in simulating a differential equation is just go ahead and put this into a standard form. So what we'll do is just divide over the tau value on both sides, and then get it into a dy dt form, and then a function that we'll make will be able to return dy dt for any values of u, k, tau, and just return those as dy dt. So let's just do the simplest one first. First thing, I'll probably need to import numpy as np, and then I'll also import scipy.integrate. I'll do from. Okay, and I'll just import the ODEINT package. And then later I'm going to also want to plot some of this as well. So I'll do matplotlib .pyplot as PLT. And if you're in this environment, just make sure you do %matplotlib inline. Okay, you don't have to do this if you're in something like Spider or you're just writing a .py script as well. But that'll allow you to display the plot there in the web page. Okay, so this is just kind of my header information, just some packages that I need to load. And if you do Alt-Enter, then it'll give you a new cell below it. Okay, so the first thing I want to do is just create a new function. I'll just do first order system, and then this is going to be a function of y and t. And then what I want to do is return the value of my derivative. Okay, so let me do this. I'll go ahead and define my tau value equals to 5, and then my k value, we'll say that's equal to 2. And then what I want to do is return dy dt. Okay, so dy dt in this case is just going to be equal to negative y plus k times u divided by tau. Okay, and then I also need to find my u value here. I'll just say that steps up to 1. Okay, so here's my function that I have defined, and now I want to integrate it forward. So y is going to be equal to ODEINT, and I want to integrate this first order system, and then the next argument is going to be my initial y value. Okay, so let's say I'm starting from 0. Okay, for that y naught value, the y value, it's going to be on just right when I start. Okay, that's going to be y naught, and then I'm going to integrate to find y of t. Okay, so the other thing I need is a time span of where I want to see the simulation. Let's say I want to go up to maybe a time span of 10. Okay, I can just put 10 there. And then if I hit enter, okay, or alt enter, and then I print y, okay, and then that's going to be 0. Okay, I think I need to do a time span here. Let me do 0 to 10. Okay, and then I will print my y. I'll do just a control. I'll just do an control enter. Okay, so it gave me the value at 0 and then 10. But let's say I want to see some other points as well. Okay, so let me just go ahead and put 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I have all those values in there now. And I'll hit control enter and then come down here and hit control enter again. And I'll see the value of y at all of those points. This can be just a little bit tedious. Let me go ahead and delete this one. How do you get rid of a cell? Okay, I know there's a way to do it, but let me go ahead and just use that one. Okay, and I will say t. These are going to be my time points, and I'll do numpy linspace, and I'll do that between 0 and 10 and do 11 points there. Okay, so let me just go ahead and put in time instead. That just created that vector that I just saw. Okay, and then I'll do, I'll just print y right here. Okay, and let's see, t is not defined. I haven't run this one yet. Let me run that one and then run this one. Okay, so there I got the same answer. Okay, so this is, I defined this function called Firstorder. I said t equals linspace, linearly spaced between 0 and 10, 11 points. So that gives me 0. I'll just print that out too. Okay, so there are my values of t, and then there are my values of y. So now let's say I want to plot this, then I can just do plt plot and do t and y. Okay, and there's my plot. Okay, but let's say now I want to have that u value change maybe at different times, okay, in that horizon, or I might want to change my k or my tau value. Okay, so let me just come back up here, and let's say I want to have a different k value. I want to be able to input that, and maybe a u value as well. So I'm not going to define those here. I'll define these beforehand. Okay, like maybe right down here, and then feed those in as it's integrating. Okay, so the thing that I need to add here is args equals, and then I'll have k and u there, and then I can add those in as arguments. Okay, so since I've changed a few things, let me just go ahead and run all again. Okay, so it'll give me the same answer there. Okay, so that's how you input these optional arguments. Let's go ahead and also step through this in just a little bit more detail. Let's say I wanted to just step through and maybe change the value of u at every time point. Okay, where u might be equal to, let's just make this zeros, and we'll do that the same length as time. Okay, and so if I just print u, then I just see I have 11 zeros there. Okay, and if you also print length of t, you'll see that equals 11. Okay, just like I defined right up here. Okay, so now what I want to do is maybe step that up after 3. Okay, so 3 to the end, we're going to make that equal to 1. Okay, and then let's do this. Let's go ahead and print U now. Okay, so you'll see it's 0, 0, 0, and then you know, the 3 is actually the 4th element. In Python it starts with 0, 1, 2, 3. Okay, and then there's 1s after that. If I just specified it, you know, 3 to 8, then only some of those would be equal to 1. But if I just leave that final number out, it just knows to go to the very end. Okay, so I have different U values now, and I want to have those input at different times in the horizon. So let's first of all just go ahead and create a for loop for I in range length of t. Okay, that was 11, and I need to do it -1 because I'm only going 10 steps. Okay, and then I want to integrate this for the first time step. And so that's going to be not all of those t values, but that's only going to be between ti to ti plus 1. Okay, so I created a little vector there that says, you know, these are my new time points. Okay, so I'll just create time sample points, okay, and then I'll put that in here as ts. Okay, so there I have, it's going to loop through and just, you know, calculate these, and then let me go ahead and just print, you know, y, just that when it solves that. Okay, so and the other thing I need to do is just change this to y naught, because that initial condition is also going to change as I start calculating. So the thing that I need to do initially is just put let's see, y naught equals 0, and then after it integrates, my new initial condition is going to be y1. Okay, so you have y0, which is that initial condition, and then y1 is going to be the final condition, and then it'll feed back in. The next time it goes around, it'll feed in the new initial condition and recalculate that. Okay, so let's just go ahead and print out y1. Okay, and we have y0 not yet defined. Okay, I forgot to run this one up here, and then let me run this one. Okay, so size of an array returned by f does not match the size of u. y0. Okay, let me go ahead and just print. I've got some other error here. Let me go ahead and check this one out. And print y1. Okay, I've still got one other one. Let's see, why not? So it looks like I had an error. Size of the array returned by f does not match the size of y0. Okay, so let's go back up here and see. Okay, so let's see. See if I'm doing anything wrong here. Oh, you know what? It's because I put a vector in here and it returned a vector of dy dt. So this one I need to put in ui. Okay, so it's going to use that just the value of u. I changed this one to be a vector instead of a scalar, so I just need to put in one value right here, and that's where it was choking. Okay, so and that message came through because it said the size of the array returned by f does not match the size of y naught. Y naught's just a single number, and it was returning 11 numbers in the dy dt. Because I passed in a u here that was 11 long, so it passed it in here as 11 long, and then made this 11 long as well, and returned 11, but it said, whoa, I only have one state. What are you doing here? So anyway, there's my, I just go cell, run all. Okay, so I have you know, some of these numbers now. Now this one you can see a little bit of a delay before it starts going. Now I need to store these numbers. So to do that, I'll just do y storage equals numpy. Let's just do zeros, and we'll make that the same length as t. Okay, and then y storage. The very first one, the initial condition, okay, just the very first element is going to be equal to y naught. Okay, and then we'll just store this each time we go through. Y storage, and this will be I plus 1. Okay, that's going to be the next one in that list. That's going to be y naught. Okay, so all right, let's go through this. I may get a, let's see if I've got this. Okay, so let me go ahead and run this one again, and then run this one. Okay, and then we'll plot y storage. Okay, so there we go. We started the input after 3 cycles, and there you can see you got a little bit of a delayed response, and then it started responding. Okay, so here we have our function is the same that we had before, but now we're just inputting these parameters right here. We calculate the derivative, we return that derivative, and then these are the inputs to that that we need to be able to integrate this. Okay, the time, the k, the u values that we want at each individual time point. Then we set up this loop. So instead of solving all of those times all at once, we only solve one time interval at a time. That allows us to put in different u values at different time points. Okay, so that's going to be important. For example, when we set up a PID controller, or other things where we need to loop through and change things based on the input based on how the output is changing. Okay, so this is kind of a primer example. What I want to do is maybe just get to a little bit more complicated one, and what we're going to do on this is just come to the course website for the process dynamics and control. Just go to APMonitor.com/PDC, and we're just going to take a look at this blending application. Okay, so we have in this blending application, we're going to create a dynamic model based on physics-based derivation from balance equations. So these show up all over the place in engineering for the dynamics, where you're mixing things or processing them. You have reactors, liquid levels in tanks, energy balances, maintaining a certain temperature. So they show up all over the place, and we want to develop some equations that can describe the dynamics of how, in this case, the feed temperature of the reactor and the feed concentration of the reactor affect the outlet temperature and the outlet concentration. So if you want some more information on species and energy balance equations, just select this, and it'll go through kind of how to build these and work with them. So what we're going to do here is, here's the species balance. Okay, so this is like an example. I'm showing you how to do it first. I start with this, this species balance right here. Simplify it out. We have terms that we can cancel out, and then we also put it in terms of concentration instead of moles as well. Okay, and then here is the script that we use to solve that equation. So it's very similar to the one that we just solved. It's a first order system, but it's just a little bit more complicated. Again, we have our state x, that's a concentration in the time, and then we have our feed temperature and our concentration of our feed as well, and then we're just returning the derivative of the concentration with respect to time. Okay, so here are some initial conditions as well. Okay, so initial condition is there's initially no concentration of A in the reactor. We're going to start feeding some in. There's our initial condition for the feed temperature as well. And then, the initial condition of the reactor. Well, actually, this one is the feed temperature. The initial condition of the reactor is going to be 350, but we're going to cool it off. Okay, and then we're going to start feeding in a concentration of A of 1, and here's our time interval from 0 to 10. This should actually be in hours, I believe. Okay, and Okay, and then we're using the same ODEINT type function with our model name, initial condition, time values, and then these input arguments, and then we calculate CA. In this next step, what we're doing is we are just putting all of the values that we want to export into this data matrix. Okay, and this one, what this matrix is doing is when it calculates the concentration. Okay, so we have a very similar equation, but it's going to be d concentration of A, d time. Okay, and then that's going to be the volumetric flow divided by the volume times the concentration of A feed minus the concentration of A leaving. Okay, so we're simulating this one, and when we use the ODEINT, it's going to then give us a concentration of A with respect to time. And then we also have time as well. So if you think of this just as like a little table, okay, and then these are the values that then we want to put into data.txt. So what we're doing is we're just stacking those together. We put time here, we put concentration there. Now when we put them together, they're both row vectors. So you have time is like that, and concentration of A is like that. So we use the V stack, we vertically stack them, one on top of the other, put them into a matrix, and then we also have to transpose them. So the dot T, when we do that, that just shifts them, so it transposes them so they're in column vectors instead. Okay, so then the final step is we just plot the results, and then add some things like Y label, X label, and legend. And so what we're going to do is we're just going to start with this code, and then we're going to add the energy balance to it. Okay, so just go ahead and grab this code from this address, and you can come down here and select the get code option down there at the bottom right, and that'll pop up a the code in kind of text format. Go ahead and copy that out, and what I'm going to do is just go ahead and put that into my let me see, I'm going to create a new notebook. Okay, let me put my mouse over it. New notebook. Okay, so there's a new one. Go ahead and just copy this in. Okay, and you don't need the show at the end if you're using the IPython notebook, but you do need to add the matplotlib inline, just so it'll show up in your web page versus doing a pop-up for you. Okay, so go ahead and just run this first of all. If you run it, you'll see the concentration versus time. So we have this differential equation right here, the concentration versus time, but now we want to add this energy balance as well. Okay, so we have, we're going to simplify this down just a little bit before we begin. The way we'll do that is make a couple assumptions. Okay, so the first one is that the mass is equal to the density times the volume. That's pretty straightforward, and the mass flow rate is going to be equal to the density times the volumetric flow rate as well. We're also going to assume that we have no heat input to the reactor and no shaft work being done on the fluid. So we're left with a density times the volume times the heat capacity of the fluid, d temperature, d time. Okay, and then we have the density times the volumetric flow rate times the heat capacity in, then we have I'll just do temperature in minus temperature out, assuming that the heat capacity is going to be the same in and out. And then let's just assume, well, okay, so heat capacity is going to cancel, density is going to cancel as well. And so we're just left with v times dt equals v dot. That's also sometimes used as q. Many textbooks use q for volumetric flow rate. And then we'll do T in minus T out. Okay, so there's our energy balance equation. That's the one that we want to add to this application right here. So let me go ahead and put this over here so that it just kind of keeps in this window. Okay, so in this case, I'm not going to start from scratch on this, but what we're going to do is just augment this to give us two states. In this previous example that we did right here, and also in the first order system, we only had one state. So it becomes a little bit trickier with two states, but we're just going to add a second one. I think we've got all of our all of our variables there. Okay, so our states, in fact, we are going to have two. So we're just going to modify this function that gives us our derivatives. So we have two equations. One is v dca dt equals q times ca in minus ca. Okay, so there's our first equation. We already have that one there, and we're just going to add this second equation as well. Okay, so let's start with our second state. Okay, so this one's going to be temperature. Okay, it's going to be temperature of our reactor, and let's just rename that as T equals x1. So what we're going to do is this function. Okay, this function, and we have mixer. There's going to be some input arguments, and the two that are required are going to be the states and then the time. Okay, and then what we're going to do is we're going to return dx dt. Okay, so if we give it the states and we give it the time, we need this to return a derivative. And so really all we're doing with this model is just filling in the details between the inputs, the states, and the time, and the dx dt. So to do this, what we're going to do is calculate dx dt1 and dx dt2, and then we'll return a vector of dx dt1 and dx dt2. But if you add more, you just add more elements to that vector. Okay, so we just have to break it out here just to give, instead of dealing with x0 or x1, we just want to give those better names so we can we can work with them, and maybe they're just a little bit easier to remember which one is which. Okay, so we have CA and then dt. I'll just copy this and add our dt. Okay, and that's going to be a temperature feed, and we don't have that. Oh, we do. We already added it right up here. That's one of our inputs. Okay, and then minus temperature. Okay, so we have two things that we need to return, not just one. Okay, and so I'll return dt. Okay, so we're returning that. Now if we just ran this, we could plug in these four values at the top, the arguments, and get the two values, the derivatives, out. Okay, so it's just a standard function. There's nothing special about this. But then we're going to come down here to the initial condition. We need to add another value here for our initial condition, which is going to be the T naught. Okay, so let's do that. I'll just do T naught equals, and then we'll put that at 350 degrees. And okay, and let's see. And then the other thing we need to do is this is going to come back as, I'll just put that as Y. And then it's going to come back as a, after it solves it in ODEINT. So you give it a, the times where you want to solve it. This might be 0, 1, 2, all the way up to whatever it might be. and then you're going to get a y result, okay, which is going to be in this first column. It's going to be, the CA values at all those times, and this one is going to be all the temperatures at all those different times. So then we need to just split this up. So what we'll do is just say CA is going to be Y. We'll take all the rows and the very first column. So we're going to take this very first column right here and just call that CA. And then the next one that we'll do is temperature, and we'll just grab all of those and put those in, the next column. Okay, and then maybe we want to store temperature as well. I may need to transpose that one as well. I'll go ahead and just run it and see if I need to do that or not. Okay, and then we'll plot the results. Let me add another subplot here. So before I was just doing concentration, and if I do a subplot, this is the number of rows, number of columns, and then which number I'm on. So I'll do the first one. So I want one column of plots and 2 rows. So I'm just going to create 2 subplots, and okay, I'll just do that. I'll leave the X label for the second plot. Change that to 2. That's going to be my second one. And then let's plot the temperature. Capital T is case sensitive, and I'll do a blue dashed line, and I'll call this temperature and put that in Kelvin and temperature. Okay, so what we've done is essentially just augmented our model with another input and another output. Okay, so the output's our derivative value. It's going to be these 2 equations right here. And then we just gave it another initial condition right here. Okay, and then it's going to return the solution to this y. I just had to split it up into these 2. Save it as my text file, my data.txt, and then plot the results. Okay, so let's see where my first error is. Okay, wow, okay, it worked first time. That rarely happens. Okay, but here is my temperature and concentration versus time, and you can see it starts at 350, and then as it mixes, you can see these mixing calculations happening, and then it goes to the feed temperature, which is 300. So that makes sense. It's a big tank. You've got a pretty small flow rate, so it's going to take a while for that temperature to come down. Okay, so this kind of concludes the the simulation of these. In the next video, what I'm going to do is implement a PID controller. So we'll go through and kind of make the for loop thing, kind of like we did with the the first order system, and then at every time step we'll have a set point and an error from that set point, and then adjust the maybe the feed temperature or something like that to control the temperature in the reactor. Okay, so and I'll post this video as well. I'll post it right here so you can see the solution to this and follow along with that.